Hello, everybody. This is Glenn McGilvery, Managing Director of the Institute for Catastrophic Loss Reduction. Thanks so much for joining us today. We put this presentation together pretty quickly, given the event just occurred on the 15th, and we got great response. Over almost 200 people have registered. We're currently sitting at 135 and growing. So thanks very much for tuning in. We're really fortunate to have with us today Dr. Gregory Kopp from Engineering, University of Western Ontario. Greg's been with us many times before, talking about the Angus tornado, Hurricane Irma, the Dunrobin in Ottawa, Gatineau tornadoes of a couple of years ago. And here we are again talking about yet another damaging urban tornado. Greg is ImpactWX Chair in Severe Storms Engineering. He's also a project leader for the Northern Tornadoes Project, and he's been on talking about that project a few times with us. Anyway, with no further ado, I'm going to flip it over to Greg. So Greg, please take it away.
Well, thank you, Glenn. Good afternoon, everyone. It's a pleasure to be here. I have about, just so you know, I have about 55 slides, so I'll probably talk for about an hour. And in terms of the outline, I'm going to talk about, I'm just going to give a brief introduction to the Northern Tornadoes Project, which helps people to understand our methodology and approach for gathering data after tornadoes. I'm going to give a summary of the events of July 15th. Then I'm going to talk about Barrie in particular, and I'm going to talk about some issues in particular that we observed from houses in Barrie. I also want to talk a little bit about research we're doing to help you understand how tornadoes are assessed and how we determine wind speeds in them as something that's important for future development and better understanding of how to mitigate damage in tornadoes. And I have to start with the generous funding from ImpactWX, who helped us found the Northern Tornadoes Project, and without them, this work would not be possible. The goal of the Northern Tornadoes Project is to determine the actual tornado occurrence rate in Canada. Currently, Canada averages about 60 observed tornadoes per year. My colleague Dave Sills has published a paper that estimates it could be upwards of 200, and that a lot of the tornadoes are being missed. And that was really the motivation for forming the Northern Tornadoes Project, was to get a much more accurate count of those tornadoes and get detailed data for all of them. So part of the challenge with that is we want to find tornadoes in remote areas, in forests, in croplands, and grasslands. And I'll talk a little bit about that further, because that's an area of active research. But we are finding more tornadoes as a result of this concentrated effort. And why do we want to know all that? Well, there's a lot of risks for the insurance audience. Obviously, a better handling of risk of tornadoes is important. And a lot of the most severe tornadoes occur in outbreaks, such as the events of July 15th. And so getting a better handle on the true count and the true climatology of tornadoes becomes quite important. It's also important for understanding warnings. So when Environment Canada and others issue warnings, we can provide ground truth for what's actually happening after the fact to help with that. And also for engineering studies, and I have obviously come from the engineering side of this, and I'm going to be talking more about housing performance and engineering and what we can do to mitigate damage. We also like to raise public awareness. We think that's important, and there has certainly been a lot of public engagement with this most recent tornado. We have a team that is growing. Dave Sills is the executive director of the project, so he runs the day-to-day operation and manages everything. And we have a team of meteorologists and engineers collaborating. We have full-time staff and a series of doctoral students and one postdoc that are contributing to the work. And our Western partner, University of Manitoba, John Hanasuk, leads survey teams out of Manitoba. We also have partners with various other organizations, including the Weather Network and Instant Weather and Cat IQ. And a lot of we do a lot of coordination with Environment Canada regarding tornado events. So that's really who we are. In terms of the research, I'm going to show some of the work later. We collaborate with an international research team to get better understanding of tornadoes, their intensity, how to detect them, and all of that. So we have experts in social science, in soil science and geotechnical engineering, and trees and crop damage and LIDAR and other remote sensing tools, machine learning, and all of that to put it together. And I hope that research part comes through at the end of the talk. but we use all of that to improve our methods continuously. So what do we do? Well, we're trying to identify tornadoes across the country, and we've developed a set of criteria, which I'm going to talk about. And really what we can do now for the first time is apply a consistent set of metrics to identify tornadoes across the country. For us to classify an event as a tornado from a photograph or from eyewitness descriptions, we need some pretty significant evidence. We need a well-developed funnel cloud extending fully from the cloud base to the surface, or a funnel cloud extending partly to the surface, but we see debris near the ground. We also are classifying water spouts as tornadoes. Previously, within Environment Canada, the marine and overland warnings were examined separately, and so water spouts were not included, but other places in the world, like Europe, include water spouts as tornadoes, and we've started doing that too. We also use other methods, and so we classify a lot of tornadoes just based on damage observations. And so what we are looking for with that are tornadoes leave damage paths that tend to be long and thin, and you'll see that in some of the photographs that I'll show you later today. We need a path length of something at least a kilometer long. If it's shorter than that, it's hard to say what it is, and a maximum path width of 2 kilometers or less, although some very large tornadoes can occur. Often these have been seen in the US as big EF5 tornadoes, and we had one tornado that was 2.4 kilometers in our database from a tree from a event in a forest. And so that's how we classify tornadoes. They're also in thunderstorms, you can have downbursts. And so this is really cold air falling out of the sky and impacting the ground, and it tends to move out radially. If it's smaller than 4 kilometers, we call it a microburst. If it's larger than that, it's a downburst. And if we don't have enough evidence for a tornado or a downburst or a gustnado, for example, we classify it as unclassified wind damage. So we're really trying to detect all the wind damage in Canada, but to do that, to get tornadoes, we need to really look at all the damage. And of course, if we have both visual evidence and damage, it makes classification much easier for this. The Northern Tornadoes Project also strictly follows the enhanced Fujita scale, the Canadian version, which Dave and I helped to implement within Canada. And it's important to note, I'm going to talk a little bit more about this too, that if there's no damage in a tornado, it's just rated as EF0. So wind speeds in tornadoes are categorized by the damage they cause. And so they tend to be lower bound estimates of the wind speed if we can see that damage. And we like to do ground surveys. This is especially important when it's in urban or suburban areas, but that gives us the most accurate. We're also spending a lot of time looking at forests, and we use tech tools like drones and satellite imagery to help with that. But within forests, damage is usually limited to EF1 or EF2 because of limitations that we have in the EF scale. And again, that's a topic of research I'll talk about. So we're working on improving the EF scale, but right now we follow it rigorously in assessing the Canadian tornadoes. So on our website, you can see all of our data. We have we have open data policy, so everything we do is accessible. Last year, we had 409 investigations of wind damage, which resulted in 339 events, 77 tornadoes, and then the tornado experimental, those are tornadoes over water spouts, and we had 26 of those. So if you put those together, we had over 100 tornadoes last year and over 100 downbursts. So more downbursts than tornadoes last year, which we think is a little bit unusual. And so that's what we do. We conducted a lot of satellite analysis for 292 events. We did ground surveys even through the pandemic. We had permission to travel in Southern Ontario, and we did 31 ground surveys. I think we must be approaching that already this year, the way our team of engineers has gone out. And we're doing more and more drone analysis to capture data. So the tools we use for this project, we use a lot of high-res satellite imagery, which has a resolution of about 3 meters per pixel. In remote areas, we'll fly aircraft over, which gives us a resolution of about 5 centimeters, so it shows a lot of detail. And if we can drive to an event and there's roads near it, so we can fly our drones, we can get about 2 centimeters resolution with that. We do also unique aerial analysis for tornadoes, a Fujita style. Fujita did these amazing drawings of damage that you could see in crops and even in dirt and soil. And so we're able to use that kind of analysis now too with these tools. We've also developed our own app. And so all of that, we can get live updates when our tablets are connected, when we have phone coverage, and we can capture all the data from that. Then this data gets put into our website. It's permanently archived and in deep storage, and a lot of the more common things that people might look at are in shorter term storage that you can access very, very quickly through the dashboard. And so here's many of the tornadoes we've had through 2020. And so you can see the events and the coverage that we've had. We've done surveys in the Northwest Territories, and we've identified tornadoes now as far east as Nova Scotia, and Newfoundland had a water spout last year, which again counts as a tornado now. So we've spanned the country with this. There's a lot more interaction on our website. We work on continuously upgrading it, and you can see a lot of details. So if you're very interested in the details of events, you should be able to find some very good information, photos and details on these types of events now. And if you want more information, you can of course contact us, and a lot of our high resolution drone imagery and things are publicly available. They're just so large that we don't make them available on the website. So on to July 15th. So on this day, there were 6 tornadoes, and they're mapped here. All of them are rated EF2. Of course, the one that we're going to talk about in great detail is the Barrie one. I'm going to turn on my laser pointer here. Over here, but we had even up quite far north in a forest. I'm going to talk about the Lake Traverse tornado as well, which was EF2. And we had some across the lake from Barrie, a separate tornado, Laurenville tornado, and Little Britain down here. Again, it went through mostly farming region in the Kawarthas. So that was a summary of the event. 6 EF2s in one day is a pretty rare occurrence here. Of course, Barrie's been hit before in 1985, and on that day there was more than 10 tornadoes, two F4s, of course the one in Barrie and also one in Orangeville, a couple of F3s. It was the Fujita scale back then, so just F3, 7 F2s that day, and then a couple of others, weaker ones. And so that was a really significant event. Of course, that was over 35 years ago now. In terms of how often multiple EF2 tornadoes or stronger occur, my colleague Dave Sills looked back into the database, and since 1933, this is the 10th time we've had at least 3 EF2 tornadoes on one day in Ontario. The most recent was in 2018 when we had the tornado outbreak in Ottawa Hull, and we had the F3 Dunrobin tornado that particular day. And so it's not uncommon to get this many tornadoes, but it seems to be something that occurs about once every decade to get this many F2s or at least this many F2s in one day. So let's talk about Barrie a little bit. This was a significant tornado in terms of the amount of damage caused. There was a couple hundred houses damaged. There was 11 reported injuries. We conducted a detailed damage survey. We were there a few hours after the event, and we're there for a couple of days doing assessments. I'll talk about the details of it, but we assessed it as a high EF2. So we estimated 210 kilometers an hour based on damage to a couple of houses in particular. Path length was about 12 kilometers, extended from approximately the Highway 400 to the lake, and the maximum width of it was about 600 meters. And there was media reports that in the immediate aftermath, 70 houses were uninhabitable. It's not clear yet how many will be condemned and be bulldozed, but we have well over 20 houses that are at EF2 levels and sustain major structural damage. Just a little bit of the meteorological overview. Again, this is not my expertise. I'm an engineer, but there's radar imagery of it, and the tornado was visible in the new radars that Environment Canada has established. There was a tornado signature already at 2:23, and tornado impacts in Barrie around 2:35, about 12 minutes later, and the Environment Canada warning came a little bit after that. There's been a lot of discussion about warnings and the efficacy of that. And one of the things we are trying to do with Northern Tornadoes Project is work on tools to help with nowcasting of tornadoes as well. So that's something that we'll be working on over the next few years as well. There's video of the tornado. It was hard to see, but this came from Twitter. So it's not the most dramatic looking from the perspective of the video, but that was it. And then afterwards, of course, there was the impact. So we're looking over here, this is a drone photo, looking over the most severely damaged area at the bottom center part of the photograph, and the damage track progressed eastwards towards the lake. There was a mobile home park near the lake where there was also some significant damage, a couple of roofs off, but the large trees you can see in that area, I think, help protect those mobile homes in that area. So the most significant damage, and what I'll be talking about, is in Barrie, in this area here. I'd also like to note that on the other side of the road here, there's no houses at all. So if the tornado had moved a few hundred meters to the south, we wouldn't be talking today, because we would have had probably a nice tornado, but going through farmland and not doing much damage overall. So satellite imagery and some of the damage survey information. So this is a map of the damage, and we went through house by house very quickly from the street and assessed the damage from it. We also used the drone imagery to help see backyards and roofs. The red dots are the most severe damage, EF2. If you count those up, there's 25 or 26 of them there. And most of those would be associated with a roof off. So there was about 25 roofs off in Barrie. Widespread EF1 damage. So these are lower wind speeds. There would be shingles and sheathing and siding, and those kind of things are damaged. There was a lot of broken windows, as I'll show in some photographs. And then EF0 is kind of threshold of damage kind of thing. So you see it scattered about, and that's fairly normal in tornadoes, is that you have that range of damage. There was a few hot spots at the west end, in the central portion of this neighborhood, and then at the end of it. And so there's quite, it's quite an interesting and complex damage path from this tornado. So I just want to talk a little bit also about how the tornado is rated. So the damage indicators here in the photograph were all houses, and the EF scale has this. So we have something called degrees of damage in the EF scale. And as the degree of damage increases, it goes with kind of the failure sequence of how things happen. So degree of damage 1 is the threshold of damage. So there's things that are damaged by the wind, but there's not much, and that's expected to start happening around 100 kilometers an hour with houses. You start then to lose your eaves troughs and vinyl siding, and that estimated to occur around 125 kilometers an hour. Then you start to get broken glass and doors. You have things flying through the air from debris. You get breakage. That happens at a bit of a higher wind speed. DOD4 is when you start to get some more serious damage, and you have roof sheathing loss and things like that happening. DOD5, the entire house shifts off the foundation. This is in the EF2 range, but this often is associated with houses that aren't bolted to the foundation. And we sometimes call these sliders in our surveys. You see this much more often in the US than you do in Canada. Then the EF2, the major EF2 damage is DOD6, when large sections of the roof are removed, but most walls of the house remain standing. Then DOD7, you have exterior walls collapsed. We had a couple of these. I'll talk about that in a few moments. Exterior walls collapsed after the roof is off. That tends to be the failure sequence, and that's over 200 kilometers an hour. And then from there, the damage just grows. And an EF5 tornado is based on houses, and you have destruction of a well-built, well-constructed house. and everything is destroyed and it's swept away. And that's estimated to occur at about 320 kilometers an hour. So within that, so what we do is we observe the damage. We use the expected values. If we have some reason to lower it, for example, if we think that there was poor construction or there was some kind of reason to think it was weaker than it was, we have a lower bound. And if we think there was some reason to believe it should be higher, we would use that. And so that gives you kind of the range, but we typically would use the expected values. So we identify for each location. And then the EF scale categorizes these. An EF0 tornado is between 90 and 130 kilometers an hour. So each scale band has a range of roughly 40 kilometers per hour. EF2 is in the range of 180 to 220. And we assessed this to be at 210. So this was an EF2 tornado. So let's look at some of the damage in more detail. I'm going to focus on a few cases here to help you understand some of the impacts and what we're looking for. And also hopefully a takeaway from this is that you understand that we could probably mitigate much of this damage with some fairly simple measures. So I'm going to talk about this house at some length, which lost its roof. The roof slid off the walls partially, but remained on the house, as you can see. I'm going to talk about this house here, which was the first story collapsed. So I'm going to look at that and analyze why that likely happened. So we'll talk about that in some detail. This house here was one of our higher wind speed failures with DOD7 for houses. It's the house here on the right of this inset photograph. You can see the roof is gone, and many of the walls are gone in the second floor. And so that was assessed as DOD7, 210 kilometers per hour. So if we go back to the EF scale, we looked at that house. We picked out the exterior walls collapsed after the roof is off, and we couldn't find evidence to change anything from the expected value. So we went with the expected value for this house at 210 kilometers an hour. There is one other house in that category. It was right here. It was right at the end of that neighborhood on the far east side of it. Here you can see the whole second floor is gone. Photograph from the ground here. So what's left is the first floor of the house, but the second floor is gone along with the roof. Again, to understand the failure in detail, we would have had to spend probably a day sifting through the debris here to find all the roof trusses and the walls and try to identify nails and connections and things like that. But there's just not time to do that kind of analysis. So this house was also assessed as a DOD7 and 210 kilometers an hour. So that was the basis for the rating for Barrie. I want to talk a little bit about construction issues in toenails. I've talked about this before. It was especially prevalent in the Angus tornado. I think this tornado was stronger than Angus. There was more widespread destruction. The debris field was way worse, and that could partly be due to having over 20 houses with roofs off and all of that debris entering the wind field. But it felt like a more intense tornado, and the rating here was a bit higher based on this house that's on the right side of the photograph. I want to talk about this house right here. This is the one where the roof slid off. You can kind of see the sheathing there through the window where the roof is, in the back corner of the roof over here on the left. So first of all, just to get everyone on the same page here, the building code in Canada requires the roof trusses or joists to be fastened to the top of the wall with toenails. So toenails are these angled nails. They're not the things at your end of your feet. Little joke there, probably not funny. But it's 3 nails that are put in at an angle that you can see here. And so that's what holds your roof to the walls. Of course, when the wind is blowing, it's important to realize that wind wants to lift the roof up. And the wood frame roofs like this are very, very light. And so what's really important for holding the roof to the walls are these 3 nails, and they go at the end of every truss. And that's what's responsible for holding the roof in place. In this case, this is from a lab-based testing, and you can see the nails after we've pulled them out and determined their strength. But that's what's holding the roof in place. So why do they matter? Well, as I said, wind causes uplift on the roofs, and we need to be able to hold them down. It's the same physics as gets an aircraft into the air. It's somewhat counterintuitive for people. We think often of well-built houses as having sturdy walls that hold up the roof so the walls don't collapse on us. And that's mostly true in Canada, where we need to consider snow loads, of course, but wind is kind of opposite, and we need to hold the roofs down, and that's what makes the house resilient in the windstorm. So when the roof fails, walls are vulnerable to collapse. We saw this in Barrie, and this is a significant life safety issue. I'm amazed over and over how I think we get lucky and we don't have much loss of life from tornadoes in Canada. I'm grateful for that. But when walls collapse, this is definitely a life safety issue, and it's something that building codes deal with. The other problem is that when the roof fails, it wants to fly away, and it impacts downwind homes, downwind cars, and this leads to a cascading set of damage. So you have one thing fail, it hits other things, they fail, and you have more and more debris entering the wind field. Debris travels at amazing speeds, and things like a piece of plywood traveling at 60 or 70% of the wind speed that caused the failure. That's the kind of speeds we've seen when we do wind tunnel testing of debris. It's like a knife flying through the air, and it cuts through things and causes a lot of damage. Again, this is a life safety issue, and if we can hold the roof structure in place, we reduce the damage a lot, and we'll make things safer. The other thing that I think is really important to understand is that fairly recent research over the last 7 or 8 years has indicated that if we have everything perfectly installed, the weak link in the load path, so when the wind wants to lift the roof, the load path is going vertically from the roof down through the walls and into the foundation. The weakest thing there is that toenailed connection. And from an engineering point of view, that's not good practice to have such an important component be the weakest link in the structure. It's weaker than the sheathing, and it's weaker than the walls to the foundation. So if we can fix that, we will improve life safety significantly in these events. So my argument is that what is, I think, probably the most important structural component in a house is actually the weak link. And then it gets worse than that. Toenails are often not installed correctly or at all. And I caused a bit of a stir on Twitter last week. I put my tweet here just to remind people of that. When I did this, I expected 5 or 10 retweets from the usual people that retweet my work. And it went out a little bit and got into the community. But I think it raises an issue that we need to discuss and make people aware of. And that is also the issue of construction quality with this critically important component. And so I'm going to focus on this house. We didn't do a full forensic analysis in Barrie. We just didn't have time and resources to do it, unlike what we did in Angus when we could look at every single house in significant detail. But this is that roof that was left on the walls, but you can see it's not in the right place. And if you start looking carefully at the photograph for where the toenails should be, there at the end of the truss, you can see whether there should be there. It looks like there is one in that case. Over on this side, I didn't see any. And so that is a real limiting factor. And so this came off earlier than it should have, and it may have stayed on. Who knows if the nails had been there. Again, on the other side of it, looks like each of these had one nail in it as the roof was constructed. And so this is a weak link and is weaker than it should be. And again, the roof to wall connection, the toenails are a critical path, the critical element in the load path, and then it's not done properly. It's a major concern to me. I've been talking to people about why this might be and what we could do about it. And my understanding is that when the roof is constructed, they put the truss and they put one nail in place just to get it locked in place initially. And then the sheathing goes on. And if you need to adjust the the sheathing and truss position to make sure everything lines up properly, you can do that quite easily. But afterwards, then you need to go back and put the remaining nails in. And it seems to me that may be the missing step. I'm not making excuses here. It just, for the builders, it just seems like that's something that needs to have a little more emphasis placed on it. It's also worth noting that our experience in the lab is that it's very, very difficult to put in toenails correctly. In fact, as a researcher, we need to do experiments of high quality so we can publish them. We actually would often pre-drill the holes for the nails so that we could assure that the nail was in precisely the right place to get the capacity. Well, that doesn't happen and won't happen when you build a house out in the field. And so it will never be perfect. Often in the lab setting, we would crack the lumber. In the lab setting, we throw that out, but that would need to be fixed then also when that happens in the lab. So toenails really aren't a good way of doing any of this. The other part of it then is inspections, and to check these things, you need to be there at the right time. You need to get up on a ladder and start counting the nails and looking at the nails. And that also is challenging and expensive. We think there's a better solution for this with hurricane straps, which would allow the inspectors to see it. So that's what we think is something that we've been looking at a lot in the lab and we have been advocating for, is putting these in. So again, the key element in the structural load path is the roof to wall connection. Hurricane straps are these little metal plates here that get nailed in, connecting the bottom of the truss to the top of the wall. We're working with Doug Terry Holmes in St. Thomas, and Doug likes using these long truss screws, which also go in easily and very fast. I'll show you some more details in a minute, but it makes quite a bit of difference to the performance. And it takes either of these solutions, the truss screws or the hurricane ties, the hurricane straps, remove the roof to wall connection from being the weak link. It moves to the sheathing then. And you know, if we have a choice, I'd rather have sheathing off a few pieces of plywood than a whole roof as a result. And so that's one of the main things we want to look at. To help understand this, ICLR and Western have been working with Doug Terry Holmes for the past number of years. He's working with a neighborhood where every house is using these recommendations. He's using the truss screws to go in. They're quite easy to see because they're colored. It's a little bit hard to see in the photograph here because of the size of it. We also have adjusted nail spacing for the sheathing to make these elements much, much stronger, with the goal of keeping the structural system of the house intact during EF2 tornadoes and less. So that's the goal of this project. And Doug is working with us to test how they can be assembled, find ways to reduce the cost associated with it so they can do it quickly, but have something that's more resilient. So here's an example of a hurricane strap going in with gun nails. Again, this comes from Doug and his team, and you can see what's involved in putting it in there. That increases the capacity of that roof to wall connection substantially. So you can see it takes less than 30 seconds to put one in. Doug thinks that's too long. So he's advocating for putting screws in, and that's faster. It's not as strong as a hurricane strap, but it's definitely a stronger connection than a toenail and more reliable. And you can also then make sure the top plate is fastened to the wall studs, allowing for a very strong connection and performance. So this is an issue I've been harping on. Those of you who know me for a while, I've been harping on this issue. I think it's important that we get this into the building code because I believe it's a life safety issue. They're the weakest link in the load path, and we can fix that inexpensively and easily. Existing practice makes toenails problematic, which makes the performance even worse in these tornadoes, and we can fix that problem pretty easily. The next one I want to talk about is this house here that collapsed. So this was a 2-story house, and there was some reports on Twitter that it was shifted off its foundation, but in fact it collapsed. It was a 2-story house. This is the Google Street View prior to the tornado. And so we took an in-depth look at what happened here to better understand this house. So the first story collapsed, as I mentioned. There was the shingles are off, and there's some sheathing panels off, and some vinyl siding on the second floor as well. But this failure is really out of sequence for what you would expect for a well-built house to undergo. So I think it's important to understand what happened here. And basically, there's an indication here that we had a weak first story wall due to a lack of bracing. I'm not saying this house was not built to the code. What it looks like, though, is that we may have to take a good look at this for future code changes to make sure that this kind of thing doesn't happen, because again, this is a life safety issue. So from the side, I'm going to show you some detailed drawings of this. You can see that there's foam cladding. There's no wood sheathing, so no plywood, no OSB. And then the walls are fastened to a floor with nails, and that connection is there, but there's no connection across spanning that floor plate, this connection, this wood to the floor. And so this connection is also a concern to us. Here's in the corner of the house, again, the wall is removed, and you can see the floor remaining there. The bricks, it's worth talking about the bricks. Bricks provide very little structural resistance because mortar is so weak, and so you start pushing on bricks, it collapses because the mortar can't hold it together. So to have a strong brick wall, to have a strong masonry wall, you'd have to put rebar through the holes and backfill with concrete to hold it all together, and that would cost a lot more. So in this case, the bricks are merely cladding; they're not providing any structural support. So this is what the code requires. So you have anchor bolts connecting to the foundation from the sill plate. Then you have the floor joists, the floor, and then the wall. And so the wall is typically assembled on the ground and then lifted into place. And so it gets nailed to the joist. So that's what we saw in the other photographs. Here, this nail, this is what the code was requiring. So that is one of the challenges for this. We saw the same thing in Dunrobin in 2018. You can see the floor here, and then there's a discontinuous sheathing here. So if this sheathing panel went from the foundation across that floor into the wall, that would provide a lot of structural support for holding the wall and the floor in place. And so again, there's a relatively inexpensive solution for that particular connection, as we've seen before in Dunrobin. So the recommendations for that are to have sheathing that spans from the floor plate, from the sill plate into the wall. We have to have connections also between floors. Again, a sheathed house can accomplish that, and then you can have sheathing up to the ridge. We have hurricane straps at the roof to wall connection, and if we don't want to have sheathing, we need to have these interstory straps between the first and second floor and the foundation and the first floor. So those are two ways that can be mitigated. But the foam, when there's not sheathing, you need additional bracing so that the house doesn't collapse in shear. So that's something that we're looking at still in detail and doing some calculations about. I mentioned earlier with the windborne debris, that when we have roof failures, you see major structural elements cause a lot of damage. In the house on the left, there's lots of broken windows. You can see different parts have blown in actually, and the driveways, you can see lots of structural lumber on them. Again, these are structural members coming from roofs upstream and causing a lot of damage to vehicles, hitting houses, and causing further damage and cascading types of failures. I want to talk a little bit about garage doors. We saw a few things in Barrie that we hadn't seen or we don't see often in Canada. In this case, in the photograph here, the garage door looks kind of funny. It got sucked out by the tornado. So the garage door got sucked outwards. Often there are debris impacts or pressures that push it in. And then we have pressurization of the garage space, which pushes up on the ceiling and outwards on the sidewalls. But in this case, it sucked outwards, and so what that would do is possibly overload wall on the other side of the house, but in this case, the house withstood that. You can see that there was some shingles and there's sheathing loss on the other side. There was another case. In this case, the garage door went in and it got pushed in. It looked by debris. We found it at the back of the garage, but you can also see that the sidewall got blown out. There was failure above it, but the ceiling remained in place in this case. You can see that here. And so what the weak link was the sidewall in this case. And so the sidewall blew out with it. And so this was an interesting case. We hadn't seen these in earlier tornadoes in the region, in Vaughan in 2009 and Angus in 2014. And so it was a kind of an interesting case with the wall being pushed out. And there was a few cases of that in Barrie. Anchor bolts were put in. You can see the remnants of it there. And that's a close-up photograph of what was put there. The anchors were put in, but very close to the edge of the concrete. And so there wasn't much, there was good embedment from the top, but not good embedment from the side. And so that was relatively weak. You can see where that landed in the wall. So here it is. They have the washer and the bolt. That's fantastic practice. They just lined it up. They didn't quite line it up right and led to a weak link. It's not clear what would have happened if the concrete had been further in. Again, these are things that we'd have to do calculations on, and we haven't had time to do those kind of things yet. But it was an interesting failure for us. Again, little details really matter to performance, and they're things that one doesn't want to see overlooked, because those little details matter a lot to the structural performance of our houses. Let's move to the Lake Traverse tornado. This was all tree damage. There was no injuries. I'm going to show you some interesting photographs of it and talk a little bit about what we're doing to understand tornadoes that happen in forests and get better estimates of damage. So this was a photograph that Travis Farncombe took, and I grabbed it off of Twitter, but you can see the path through the forest. Really interesting patterns to the trees, and you have almost 100% fall in many regions here. So it's quite a significant damage path through the forest. You can see that in satellite. The scar is very obvious from space, and so you can see that. This is the kind of tool we use for tornadoes. EF2 tornadoes are quite easy to see from the satellite imagery. EF1 can be done. EF0 is really hard to see from satellite imagery. So this was a strong tornado that we could see damage in the forest quite easily. We have trees as a damage indicator in the EF scale in Canada. In this case, you'd have more than 80%, but in the boreal forest and in the Canadian Shield, we have relatively weaker root systems, and so we tend to be in the EF2 range for this kind of failure. What we want to do, though, is look at the patterns of failure, because there's information about the strength of the tornado in that, and so that's something that we're working with some of our collaborators. I'll give you an example here from the Alonsa EF4 tornado, which occurred a few years ago. It was EF4, and there was a house that was badly damaged there. You can see the roof and the walls and the floor are gone. People were sheltering in this house as well, and that trailer that's sitting in the garage fell from the sky and didn't hit anyone remarkably. Again, debris is such a crazy thing to deal with in tornadoes. So this was an EF4 tornado. But as you can see from the path, again, this is a satellite view, you can see the damage path very, very clearly. So we have good information from structural damage at one point, and we have forest damage. So we can correlate these two things. And our colleagues at University of Illinois, Daniel Rhee, who did his Ph.D. on tree fall analysis under the supervision of Dr. Frank Lombardo, provided this graph. And what they're doing is they're looking at they're fitting the tornado vortex and translation speeds to the tree fall patterns, and then identifying the wind speed from that analysis. So this is quite a high level analysis. They have to use machine learning to identify the trees that have fallen down. And then they do a very sophisticated analysis to assess the trees. They first used this in the Joplin tornado in 2011, and we're applying it now in Canada for the first time. The interesting thing, though, is that in that region where the house was, this method also gave an EF4 wind speed. And so this provides a way, we believe, in the long run to find higher intensity tornadoes in the forest than the current EF scale gives us. And this is a tool that we're actively working on for the future. The other part that I want to talk about is farms and crops, because tornadoes in the prairies are hard to identify. Tornadoes in any kind of farming region are often hard to identify unless they hit a barn or some kind of structure. Last weekend there was tornadoes near Windsor, and some greenhouses were hit, so you can find that pretty easily. But on crops, it's a little more difficult. But there's footprints of tornadoes there as well, and you can see where agricultural land is in Canada. This is a footprint from the Scarth, Ontario, Scarth, Manitoba, pardon me, tornado that occurred last year. It was rated EF3 based on a farmyard being hit and grain bins, but you can see the damage of the tornado here on the right. And we've done some considerable analysis of that, and I'll just talk about that briefly. So one of the ways we can use this is with different cameras. So most cameras are RGB, so you get red, green, blue, and that gives us the imagery that we would like to have. But you can also get infrared cameras, and so near infrared is a really useful tool for looking at crops. And there's lots of tools in the agriculture industry already using near infrared to identify the quality of crops and how they're doing. So we use something called NDVI, where we look at the difference between the near infrared and the red, and we do some calculations on that based on what excuse me, what a dead leaf might look like, what a stressed leaf, and what a healthy leaf might look at. And from that, we can discern where a tornado happened, because as a tornado passes over, it tends to kill the crops, tends to kill the grass, and so we can pick that up. And so we can distinguish from healthy plants from dead ones and from unhealthy ones. And so we can look at the percent change in this parameter. And if we do that for the Scarth tornado, the photograph I showed you earlier was in, I believe was in this region right here in the lower left. You can see the damage to the crops. And from that, we're working on tools right now to see if we can convert this kind of information into better estimates for tornado intensity. So that's a topic that we're actively working on within the Northern Tornadoes Project. So helping us get a better understanding of climatology of tornadoes in regions where there's low population density, low density of forests, and high density of crops, where we might be able to take advantage of that. So in conclusion, the outbreak on July 15th was pretty significant with 6 EF2 tornadoes. Again, this was only the 10th outbreak in Ontario with 3 or more EF2 since 1933. So it's common, but a little bit rare, right? It's not every year that this happens. It was quite significant in that regard. Again, the damage to houses helped us learn more about housing performance under severe weather and things that need to be fixed to reduce our vulnerability. Roof to wall connections, this is nothing new, but they're the critical element in the load path, and I think it needs to be addressed in the building code, and we've been pushing on that for a number of years. Hopefully this time we can maybe get something through again with the examples of that. And again, there's solutions for that. To design tornado resilient houses requires more than hurricane straps. There's a few other things that we need to do. The things we've learned over the years, we published a report on that in 2019 as a collaboration between ICLR and Western, and we made a series of recommendations to mitigate damage in up to EF2 tornadoes. EF2 tornadoes, I keep talking about that. Why is that? Well, EF2 tornadoes represent 95% of all tornadoes. EF2 and less represent 95%. And if you have an EF3 or an EF4 tornado, it tends to be only a small part of the damage track. So we believe a lot of the damage could be mitigated. We think this is going to be important as our population continues to grow. We don't know yet whether tornadoes will be changed in the changing climate, but we do know that our population density is changing and the amount of farmland where we have houses is changing. And so there's going to be more tornadoes hitting populated areas, and we think we should be working to mitigate that now. to that end, we're really optimistic because the CSA group, Canadian Standards Association, we're currently developing a standard for high wind safety for wood frame houses, basically for up to EF2 tornadoes. This will be a voluntary standard, but it's a consensus standard that has builders involved, it has inspectors involved, it has the engineering practice involved, and so it brings a wide range of people together around the consensus for how you would design a house to resist up to an EF2 tornado. So the takeaway from this is we can reduce the damage. The easiest things to do might be the most important, and we can reduce losses quite a lot with that. To have a fully resilient house, you have to do a bit more, and there's some costs associated with that, but we have a standard in place to do that. So I'll stop there. I do need to acknowledge again, the Northern Tornadoes project is funded through really generous financial support from ImpactWX and also from Western. And this work that I presented here, I'm just one person as part of quite a large team. Dave Sills and the entire Northern Tornadoes project team, they provided a lot of the slides for me, and they do a lot of the work, and I'm really grateful to them. I'm also grateful to ICLR and Paul Kovacs and his team for supporting our work over 20 years now, including the work at the Three Little Pigs project that we've been working on over the past 20 years. So what I'm presenting here is knowledge that's been accumulated from those collaborations over many years, and just showing what we've learned from the most recent event. So I will stop there, Glenn, and I'd be happy to take any questions if there are any.
Thanks, Greg. As always, extremely interesting. Thank you so much for putting this together in such a short time. It's fantastic. We do have a few questions, some of them brief. Right off the top, you mentioned that you developed an app. Is that an app available to the public, or is it just for your own use to do your work?
It's for our own team to use. We've been working with many people who are interested and passionate about tornadoes, and we have several people that collaborate with us and help us identify damage, often through social media. We've trained a few people to use the app that are outside of the direct team to capture data for us, but that's not widespread at this point.
Okay, thank you. Next question, and it's similar to a question I had. Why should neighboring houses experience different degrees of damage?
That's a good question. We see it all the time. We do look for correlations of damage. So there's a few parts to it. The tornado itself has large gradients of wind speed. So it's a rotating vortex. So right in the center of the vortex, the wind speed is almost zero. It increases out to a point where the wind speed is maximum, and then it decays off quite rapidly from that point. So you can kind of see an increasing wind speed in the core, and then it decreases towards the outside. So there's a strong gradient there. And so that depends on the radius of the tornado. In this case, the maximum width of the tornado based on damage was about 600 meters. So the radius right to the edge of damage is 300 meters. So there's a significant gradient even over the scale of houses for events of this size. The other part is small details in the houses. And so each has variation. And when you look at builders, you might look at the outside shape of the house and say, well, those two houses are shaped exactly the same. What's going on here? Why did one have a failure and the other didn't? Inside, they're not. So the frames and the drywall and where the nails are and where the knots are in the wood and all of that are different in every single house. So there's significant variation house to house. Often there's differences in the shapes. Two houses that are identical rarely sit side by side. And so you get this difference in performance from that.
Thank you. The next question, I think, is more of a legal and insurance question than it is an engineering question. But the question is, if the house builder did not properly install the toenails, if at all, is there subrogation possibilities, which means can the homeowner insurer go after the builder? And I don't want to answer on your behalf, Greg, but I would think that this investigation you did, as you mentioned, was not a full forensic investigation. You didn't map everything chapter and verse. I think a court case would require some pretty heavy-duty analysis and evidence, but I don't know if you want to take a stab at that, Greg.
Well, I think that's true. So we can see these things, and it's obvious to us where there's missing nails or not. But for a legal proceeding, you need more than that. You would need to be able to get into the house and to actually examine the top plates and look at everything in complete detail. So forensic analysis, you'd probably want to spend a day on each house, and clearly we don't have time to do that. What's clear to us is when we see failures out of sequence. We saw this in Angus. I remember one particular case, and I also saw it in Barrie, where you see the roof is still on, the sheathing's still on, there's some shingles off, and the sidewall has been pulled out, and it's like, okay, there's no nails there. In Angus, we went and looked, and we would count the nails. We didn't have time to do that in Barrie. In the photos I showed you, I'm pretty sure those nails weren't left in the top plate, but I cannot guarantee that to you. And so for a court case, you would need to get into the house to see those kind of details.
Right. I think we have a question from an engineer to an engineer, if I'm not mistaken, but it says, can you please comment on the resistance of the hurricane ties against the tornado-induced torsion? And a second question, what kind of mitigation measures can be applied for garage doors?
Yeah, so the torsion, well, the torsion will be aerodynamic. The tornado wind field has a bit of curvature. We've studied that in wind tunnel tests in the Windy Dome. You can see that there's a bit more, the pressures are different in a different way, leading to more torsion on the structure. That's not what you're seeing here. I think what you're kind of getting at is the rotation of the vortex is going to spin the house, and that's not what you're going to see. Even a straight line wind, you can have torsion from wind from certain wind directions. So there's always torsion in the structure. So there's nothing particular with a tornado on that at that scale of a house. Garage doors can be mitigated. You can get different quality doors. So like a single layer metal door, we've done testing on that. It fails at a relatively low wind speed. You can buy better quality doors that are multi-layer and stronger. You need to do some things to keep the tracks in place and to keep them from bending, but you can get those. They're not commonly available in Canada, wind-rated doors, garage doors, but you can get them, and they exist in the US because certain jurisdictions like Florida require it.
Right. I would say that if the door was Miami-Dade rated, if that's possible, that would be something to look at. We see those with windows and doors, other doors. And the Institute for Business and Home Safety has done some work on this area, so you may want to check IBHS out on that topic.
Yeah, we've tested too, also at the Three Little Pigs, and there's peer-reviewed papers in the public domain that can be seen on that issue.
Great. The next question: Are toenails building code across Canada? Especially interested whether it's the case in the prairie provinces.
Yes. It's the same.
Yeah, it's the same. Three per lower quarter of the truss, right? Yeah, it's the same across Canada. And my own question was just for the audience's sake, would hurricane straps replace the toenailing, or would it supplement toenailing?
I don't think it matters to me. To me, it would. It could replace. I think the builders will always want to put one in for the way they construct the roofs, and then you can go and put the straps in. I wouldn't require both for it. There's not much to be gained from that.
Okay. Any plans to submit this research to the National Research Council for possible code change? Is another question.
Yes, we've tried 3 times. So hopefully the 4th time will be a charm.
Right.
We've been learning over the years how to write code change requests, and certainly the first one we put in, I don't think we knew enough about the code process, but we do know that now, and we've been gathering evidence over the last decade for this. So I think we'll be putting it in again.
Great. Can you comment on the types of damage EF2 may cause to commercial buildings and if there are similar issues and solutions? So with regard to warehouse structures, retail stores, that sort of thing.
So yes, so in the EF scale, I don't have that in front of me right now, but there are different types of buildings in the EF scale. There's 31 damage indicators there, including all sorts of commercial buildings, including strip malls and churches and schools and car dealerships and things like that. Those buildings tend to be designed by an engineer. So an engineer has looked at it, they've stamped the drawing, and they've inspected it as it's being built. And so those would tend not to have the same kind of issues. You might always have issues with roofing because, again, little details matter with that, but they use different systems in commercial roofs than they do with houses with asphalt shingles, primarily in Ontario. So construction issues probably aren't a big issue. I remember the Windsor tornado, I forget, 6-7 years ago. There was a large warehouse and it was quite old, and there was rusted steel members, and so that building was clearly weaker than it was when it was new, and so maintenance and things like that come into play.
Interesting. Paul asks, what was the relative age of the homes damaged in Barrie?
They were, I think, around 2010 is what I heard, in that kind of range.
And he also asks whether the 85 tornado resulted in any code changes or changes in building practices.
So there was a series of tornadoes in Ontario in the 80s. There was the Blue Sea Lake tornado in Quebec, which lifted at least one cottage that didn't have a foundation, so it was just sitting on the ground. It lifted the cottage into the lake, and someone drowned, and there was many injuries. I think it's a terrible way to die in a tornado from drowning. And so that eventually led, in the 1995 version of the National Building Code, to the foundation bolts. So the bolts that I talked about earlier that I showed with the washer and not in place, embedded in the concrete. So that's where that arose from. The same evidence for roof to wall connections was available in those tornadoes, and it was clearly could be seen in Barrie and other tornadoes, but it didn't. That didn't get into the building code. So those were, to me, the two main things that had to happen. You need to take care of the vertical load path. You need to make sure the walls are bolted to the foundation, and you need to make sure the roof is bolted to the walls. And if you do that, your structure is a lot stronger, a lot more resilient. You have to do more things to eliminate all the structural damage, and it's not going to say there's not going to be structural damage in an EF2 tornado if you do those things, but it's going to be much reduced. And it's going to deal with most of the problem.
Right. Do you publish your tornado damage path online? And if so, how long after an event will you publish those?
Yeah, we put everything on our website, which is on the screen right now, uwo.ca/NTP. There's a button on the website that says dashboard. Push that button, and you'll get to the maps that I was showing earlier. Go back really quickly here. So it's not live on my screen, but you can play with that there, and you can look at different tornadoes, and you can look at different tornado paths and see the damage and things like that. So we try to make all of that available through the open data. So that would be what the dashboard looks like. You can click those buttons. So you want, if you wanted EF2 tornadoes in 2021 in Ontario, you click those buttons and you'll find it. And then you'll have things like this. We have interactive maps. These take a little longer to get put on, but each of these would have, if you click on them, you can see a photo and see some of the details. So we're trying to make a website that is interesting for people to look at, is useful for people that need the information, and have it out there for researchers. And then the full like drone imagery at 2 centimeter resolution. This is terabytes of data. We can make available on request, but we don't put on the website because it's just way too large to have transfers for. But the website is quite interactive, and if you have questions or comments about it, you can email us at ntp@uwo.ca and give us, if you think something could be done better, you can let us know.
Great. So the home that you used in the presentation that lost its roof, that was the town councilor's home, I believe. Was one of the two homes that received the degree of damage 7, and also the one that collapsed? So what was the DOD for that one?
So neither of these houses was DOD 7. The one on the left was the counselor's, the one the counselor was involved with. The one beside it on the right was the one that collapsed. You can see here, there's some sheathing off. You can see the siding off. I actually think this is a quite an interesting case because I think the siding and the sheathing from the aerodynamics will have the front end of the tornado. That's where that would have been vulnerable and that came off. And then on the back side of the tornado, the wind direction is the other way and it pushed it towards the neighboring house. You can see it collapsed towards the house on the left. So the wind was getting a broad hit, and then there was fencing there, but it was the street, so it was a little more open, and I think that's what pushed it in that direction. But both of these were, well, the one on the left is DOD 6. The one on the right is hard to assess because it's not a typical, it's an out of sequence DOD, so it's hard to assess, and that's why we're doing a detailed analysis of it. And then the one that there was two that were, sorry, it takes long to scroll through here. The ones that were EF7, this one here. So the ones we were looking at, so this was the counselor's house. You can see the red car here, the house that collapsed went in this top right to lower left, failed in that direction. It's this house here that was DOD 7. It's the one here on the right. So this one had significant damage. It had, obviously the roof is off, walls are gone, the garage door got blown in, the sidewall got blown out. It got hit really hard. There will have been debris coming upwind from these houses, so I don't know what role. We could not find the roof on this house, and it may have played a role in the failure here of impacting downwind here. It's hard to say.
So Greg, how does the building code in the US compare with the Canadian code for high wind hazard?
Depends what you compare to. So our codes are, to me, our codes are good. They're very good for snow. They're very good for energy efficiency. We have good inspection routines. I think I'm pointing out one detail that needs to be fixed, really. In Florida, they have a hurricane risk. They have pretty good enforcement of that. They have a good solid code in South Florida. If you go to a place like Mississippi or Alabama, they don't have codes. Alabama is interesting because they've actually implemented insurance measures. So they have a free market solution. Instead of having a strong building code, they have requirements that insurers must give discounts. And in that region, there's been a significant uptake of the IBHS fortified solution, which is a very high standard for wind resistance. I think our equivalent for high wind is when we have CSA 520, which should be going out for public comment later this summer. That will be our equivalent of a high wind code, but it'll be voluntary.
Right. Do you have any concerns that even if we got hurricane straps in the code, that inspectors would still miss checking for them, and just as they miss checking for toenails?
Well, there has to be an education process, and with code updates, there's usually an education process on the issues, and so hopefully that would not happen. I think it'll become much easier to inspect when you put in toenails because they're very visible from the floor. You can look and see in 5 seconds and know that it's there. So I would say to the extent that they check that foundation bolts have a washer and a nut on it, I think they should also be checking hurricane straps. So I don't think that there's any inherent problem with that. It just needs to be done.
I have a couple of other questions, but I have one for myself, Greg. Any comments on the sheathing of homes using foam insulation rather than a rigid board?
Well, that's what we were trying to understand about this other house. Let me scroll through there. So this house, I'm concerned with that, but I'm not sure how much sheathing would have helped. In the lower left here, let me get the laser pointer back on. Here you have a series of windows and not much space with structure between them, right? So there's quite a lot of windows here on the first floor, and so this needs to ensure that there's sufficient bracing to hold it up. It's also quite a large house with 2 floors and a fairly high sloped roof. I think the wind was coming from this corner actually in the tornado. On the back side of the tornado pushed it over, and so it was like at a broad face for drag and then relatively weak bracing. I think that's something that needs to be looked at often. And if you don't have sheathing, you have metal wires that get connected into the wall, but with all these windows here, it's not clear how well that would work. So this is something I think that needs to be looked at. It requires that this is a case that requires quite a bit of analysis, I think, to deal with and come up with a solution that will work. People want windows, and I think that's understandable. And high efficiency windows now with insulation are pretty effective, and so you're getting large window areas. And so the bracing of it is going to be a challenge. And so the bracing in this house needs to be looked at, but it needs more than what we can do in the 2 weeks since the tornado happened.
Right. Now, you have done some damage surveys in Quebec. Are you seeing any different damage patterns or degrees of damage in Quebec versus Ontario? Have you done enough to be able to say anything about that?
No, but we haven't had an event like this through a suburban area with a high density of houses. I guess in Hull and in Dunrobin, it didn't hit residential houses. It hit more low story apartments and things like that. So the construction was completely different there.
Okay. We had a couple of questions about shingles, including the cladding under the sheathing, I guess, under the shingles. Any comments about wind-rated shingles and whether they perform better than regular shingles? Anything like that? Do you see any differences? Do you know of any differences?
That's not something we survey in Canada. That's something that's been looked at significantly in the US, and all the recommendations from there indicate buying the better quality shingles as being more resilient, and how they get installed, I think, is an issue. I know that the National Research Council is looking at the issue of roofing right now, because shingles do come off in windstorms, and the installation is a challenge in Canada because it needs to really go on. They really need to go on a hot day. And I don't know about you, but I've seen people in my neighborhood putting them on in November. And then the tabs may not ever adhere properly, and then you get a windstorm and they'll lift up and you'll get water in, and the shingles will come off. And so that's an issue, and that's a materials problem. And I think NRC is working with the industry to find solutions for that for Canada, is my understanding.
Kind of getting back to the raison d'etre for the Northern Tornadoes project, or one of them. You do believe that there's probably a significant undercounting of tornadoes in Canada. Do you think it's on the low range? Do you think we're missing the EF zeros, ones, and twos more than anything else, or do we know what we don't know? Or
I think we're missing all of at all ranges. We've had some massive tornadoes in forests even since we started looking. I can never remember the names of them all. Brooks Lake comes to mind, and the width of it was over 2 kilometers, so over a mile, right? So these are big tornadoes with huge numbers of trees down for mile after mile. That's why we're working with these other methods to see if we can establish the higher intensities of them. Again, this is the issues with damage indicators. Is the highest rating you can get in a tornado is related to the intersection of the wind speed with the strongest thing in the path. And so we want to take as much advantage of that as we can, and so we're working on that for trees and for forests and for crops. Houses, I mean, clearly you could have stronger tornadoes than the one that's on the screen here. You could have everything wiped away, and so we could learn that from Barrie. So we probably have Barrie in about the right range. But in forests, we think we can learn a lot more from about the true climatology, and I expect things like I think we'll have more EF4s and probably EF5s in the forests, but we have to do the work with that methodology to establish that. And currently the EF scale doesn't allow that. And so that's the other part that needs to be worked on. And the US is working on improving the EF scale. There's a committee that's been working on that for about 5 years, and these methods will be allowed in that. And then I trust that we will adopt that in Canada as well. And then this kind of analysis that we're doing will get us a better sense of the true climatology in Canada.
Thanks. We're coming close to the end here, but here's another technical question. Is there any correlation to the shape of the roof, or like correlation between damage and shape of the roof? Roofs these days are being built with larger and larger exterior cantilevers and overhangs, and there's no formal design requirement for wind design. How does the shape of the roof and long overhang cantilevers potentially affect risk to the home?
So there's 2 questions in there. So the overhang, which is good for shading for sun, right, and is something that's being done for environmental reasons, is good from that point of view, but you get significant uplift on it if the wind is coming from the direction of where the overhang is. And so basically it becomes like what happens when your garage door fails and the wind rushes into your garage and pushes up on the roof. An overhang will do the same thing. The wind approaches the walls, and some of it moves upward and pushes upwards, which augments the loading from the wind pressures that want to lift up the roof on the upper surface. So those 2 things combine, and that increases the loading significantly. Shape of a roof matters quite a lot. You see in the neighborhood here, there's mostly hip roofs or some hybrid roofs where you have gable ends, like here, in combination with hip on the backside, for example. Lots of hips here. Hips are good in that they distribute the load very well, so they're very good from a structural engineering point of view, and then they should be fastened on all 4 walls, and that should be a very strong roof, a very resilient roof. For things like shingles and sheathing, there's going to be some differences, and it depends on the roof slope for that more than anything. And so roof slope plays a role as well.
I'm not sure if you can answer this question, but it says commercial and farm trusses are required to be designed for wind and likely result in tie-down installation. To support your recommendation for the installation of hurricane ties, tie-downs or similar, can you comment on how much better commercial and farm trusses perform than residential trusses after a tornado?
Well, it's not a one-to-one comparison. Like farm trusses, they're often at different spacings. They're much larger structures, and so the load distribution is different. Those get fully engineered, but they're also they'll be designed to Part 4 of the building code, and they have a lower because they're not occupied. They actually have a lower design value, so there's no one-to-one comparison for that.
Okay. I think we'll end it with one more question, if you don't mind, unless anything else pops up, but this is my question. There have been a bit of concerns expressed by home builders and home builder associations about, the push for hurricane clips and things of that nature. What do you make of their arguments against their use? They do have some concerns, perhaps legitimate, that just putting in a hurricane strap can actually lead to some problems more so than prevent them. They have an argument that these things shouldn't be used across Ontario because we don't have tornadoes across Ontario, et cetera, et cetera. What do you make of these arguments that builders and builder associations are putting forward?
Well, there's a bunch of questions in there, Glenn. There are some other failure mechanisms that can occur at the roof to the walls, but our analysis shows that those are at higher loads, and the weak link is really the toenailed roof to wall connection. And if you replace that. You're not going to stop all roofs from failing in an EF2 tornado. You have to do some other things, but it's going to be much stronger than the toenail connection is. And it's not going to cause a cascading kind of failure that makes things worse. That's just not, I don't believe that that's true. We know where tornadoes occur. We have maps for them. And, you know, I had one in here somewhere. Here's the tornado maps. And I'm going to ask you, where are the people living in Canada? Where are the people living in Ontario? And I'm going to say, well, that seems to be where the tornadoes are. On the map on the right. And so this is where the tornadoes occur, and it's where we live. So we know that, and we have statistical basis for that. If you're in the Northwest Territories, should you design for tornadoes? No, but your design wind speeds might be higher in some regions there too, and the population density is low. So again, for simplicity, it seems like let's just do it. It's not going to make things worse. It'll make things better. It's taking the weak link out of the structural system. Other things will fail, but it's happening at higher speeds and it's not catastrophic. So that to me is enough. To me, the code as a basis is all about life safety. The first codes were fire safety codes. And life safety has been part of our codes forever. I think we need to deal with this issue. I see it as a life safety issue, and the cost to do it isn't much. And I think if it was implemented everywhere and the manufacturing ramps up to deal with the demand, the cost is going to drop and the installation is going to be faster. I think the cost is not going to be negligible, but it's going to be under $100 a house by the time all is said and done and it's all settled out. So to me, that's worth it for the life safety component of it.
Thank you. Thanks for that. Thank you so much, Greg, for putting this together so quickly. I know you are super, super busy. You're doing tons of media on this. We haven't had this is the most attention we've had on this discussion ever. So it's really got some wheels and we'll have to see where it all goes. So for our attendees today, the slide deck will be on our website either later on this afternoon or probably tomorrow. The video replay of the session will be on our YouTube channel over the next couple of days. Please watch your inboxes for our next Friday forum, which is going to take place on August 20th at 1 p.m. Eastern Time. We're going to be talking about cost-benefit analysis for constructing homes against wildfire. And that will feature Keith Porter. So we'll keep an eye out for that one. Thanks again for attending today, and take care, everybody.